Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of basic electrical and electronics engineering. We'll dive into key concepts like analysis of RL, RC, RLC series and parallel circuit. Slide 1. Analysis of RL series circuit. In an RL series circuit, a resistor and an inductor are connected in series to an AC voltage source. The resistor opposes current flow without any phase shift, while the inductor introduces a delay between voltage and current. This delay is called phase angle and is due to inductive reactance. Inductive reactance, written as X sub L, equals 2 multiplied by pi multiplied by frequency multiplied by inductance. The total opposition to current is called impedance, represented by Z, and is calculated as the square root of R squared plus X sub L squared. The current lags behind the voltage by an angle theta, where theta equals tan inverse of X sub L divided by R. The power factor in such a circuit is lagging and equals cosine of theta. For example, if a 10 ohm resistor and a 0.1 Henry inductor are connected to a 50 Hz supply, then X sub L equals 31.4 ohms, and the total impedance is approximately 32.9 ohms. This type of circuit is common in applications like transformers and electric motors where inductance plays a major role. Slide 2. Analysis of RC series circuit. An RC series circuit contains a resistor and a capacitor connected in series to an AC supply. In this case, the capacitor behaves oppositely to the inductor. It causes the current to lead the voltage. Capacitive reactance, written as X sub C, equals 1 divided by 2 multiplied by pi multiplied by frequency multiplied by capacitance. The total impedance Z is the square root of R squared plus X sub C squared. The current leads the voltage by angle theta, where theta equals tan inverse of X sub C divided by R. This gives a leading power factor, which equals cosine of theta. For instance, for R equals 5 ohms and C equals 100 microfarads at 50 Hz, X sub C equals 31.8 ohms, and Z equals approximately 32.2 ohms. Voltage across the capacitor lags current by 90 degrees, while voltage across the resistor remains in phase. This type of circuit is used in signal processing and power factor correction. Slide 3. Analysis of RLC series circuit. An RLC series circuit has all three components, resistor, inductor, and capacitor, connected in series to an AC voltage source. The circuit behavior depends on the balance between inductive and capacitive reactance. Net reactance, X, is given by X sub L minus X sub C. The total impedance Z equals square root of R squared plus net reactance squared. If X sub L equals X sub C, the circuit is at resonance. At resonance, the impedance becomes minimum and purely resistive, and the current is maximum. The resonance frequency F0 equals 1 divided by 2 multiplied by pi multiplied by square root of L multiplied by C. The power factor is unity at resonance. Below resonance, the circuit behaves as capacitive, and above resonance, it behaves as inductive. For example, with R equals 10 ohms, L equals 0.1 Henry, and C equals 100 microfarads, the resonance frequency is approximately 50.3 Hz. RLC series circuits are used in tuning applications like radio receivers. Slide 4. Analysis of RL parallel circuit. In an RL parallel circuit, the resistor and inductor are connected in parallel across the same AC supply voltage. Unlike series circuits, here the voltage across both elements remains the same, and the current divides into two parts, one through the resistor and one through the inductor. The current through the resistor is in phase with the voltage, and the current through the inductor lags the voltage by 90 degrees. The total current is the vector sum of the two branch currents. Admittance, Y, is used here instead of impedance and is calculated as the sum of reciprocal values of each branch impedance. The power factor is lagging in less than 1. Example, if R equals 10 ohms and L equals 0.2 Henry at 50 Hz, then X sub L equals 62.8 ohms. This configuration is used in parallel load systems and helps in understanding AC current distribution in branches. Slide 5 Analysis of RC parallel circuit. The RC parallel circuit consists of a resistor and capacitor in parallel across an AC supply. Voltage is same across both components, while the current splits between the branches. Current through resistor is in phase with voltage, but through capacitor, it leads voltage by 90 degrees. Capacitive reactance, X sub C, equals 1 divided by 2 multiplied by pi multiplied by frequency multiplied by capacitance. The total current is the vector sum of both branch currents. The power factor in this case is leading. The circuit has lower current at resonance and is useful for designing power factor correction devices. Example, if R equals 20 ohms and C equals 100 microfarads, then X sub C equals 31.8 ohms, and the leading nature of current becomes clear. This setup is widely used in signal filtering and light dimming applications. Slide 6 Analysis of RLC parallel circuit. An RLC parallel circuit includes resistor, inductor, and capacitor all in parallel to an AC voltage source. The voltage across all three is same, and currents in each branch vary in phase. The inductive branch current lags, capacitive branch current leads, and resistive current is in phase. Total current is obtained by adding all three vectorially. At resonance, X sub L equals X sub C in their currents cancel each other. The circuit behaves like a pure resistor at this point and draws minimum current. The resonant frequency F0 equals 1 divided by 2 multiplied by pi multiplied by square root of L multiplied by C. Power factor is unity at resonance and either lagging or leading otherwise. Example, for R equals 15 ohms, L equals 0.05 Henry, and C equals 200 microfarads, resonance occurs around 50.3 Hz. Such circuits are important in tuning systems, wireless communication, and power systems.